Next, we're going to go over two theorems that give two additional properties of limit. So the first one, if f of x is less than or equal to g of x when x is near a, except possibly at a, so imagine that g is a function always above or equal to f, near this a. Then what happened here is the limit of f and g, they will have this relation here. So the limit of g is always above or equal to the limit of f, because this function is always above or equal to this. So this limit here is always above or equal to this, providing that both limit here exists as x approaching to a. Okay. Now, it's kind of intuitive, right? Because this function here is always greater than or equal to this. So the limit of that will be always greater than or equal to this, right? Okay. Okay. Now the next one here is the squeeze theorem. Now it's called a squeeze theorem, and some other instructor call that the sandwich theorem, which is more yummy. Okay. And some call that the pinching theorem, which is more painful. Okay. And I also have one student, I think he's from India, and then he told me it's also called the Penise theorem. Okay, I will explain to you why. Okay, so the squeeze theorem. Okay, so we have three functions. Okay, this is always above or equal to this, and this is always above or equal to this. So h here, g in between, and f below. Okay, so near this a, what happened here is h is the one above, g is in between, and f is the one below, so near a. Okay. What happened here is if limit of f and the limit of h as x approaching to a both exist and equal to the same number L, then this function that's being squeezed by this two function will have the same limit as x approaching to a, but equal to L also. Okay, so because g is being squeezed by this function h and f, so it has you have to go to the same limit at a. So that's why it's called squeeze theorem. Or you think about this, g is being sandwiched between the h and the f, so it's forced to have the same limit at a, and that's also equal to L here. It's called a pinching theorem here. It's like pinching over here, right? It's called a Penise theorem here. Think about it, it's like the Penise, the two Penise over here, and this suspect has no place out to go and had to go to the police station with them. Okay, okay. Now, whichever way you call that, let's just call that the squeeze theorem. Okay, we're going to use the squeeze theorem to prove this limit here equal to 0. Now, to prove the limit of this function equal to 0, let's try to squeeze this function. Think about this as the function g. Let's try to squeeze this function by a function above and a function below. Can you think about two functions to squeeze this? Right? Okay. Now, this function over here involves this part here, sine of 1 over x. Whenever you see sine or cosine, you notice that it is bounded above by 1, bounded below by -1, right? So therefore, bounded above by 1 and bounded below by -1, both sine and cosine. Okay. Now, if you multiply that by x squared, multiply this inequality by x squared, then we can find the function that above and below to squeeze this. Okay. So that's the idea. Okay. So first, so we try to find two functions to squeeze it. So that will give us an idea what are the two functions to squeeze this. Okay. So here's the proof. Okay. As x approaching to 0, see this arrow sign here means approaching to, okay, getting closer and closer to 0. What happened here is x is not exactly 0. Okay, it's just getting closer and closer to 0, but it's not exactly 0. Okay, so you can imagine this. Okay, here it's 0. Okay, and x is getting closer and closer to 0 from both sides. Now, when x is not 0, then x squared is greater than 0. Okay, it's positive. Okay, so we have the sine of 1 over x is bounded above by 1 and bounded below by -1. Now we can multiply x squared with each side of this double inequality. multiplied by a positive quantity, the inequality sign is not going to switch. So inequality sign will stay the same. Now this is a function above, and this is a function below to squeeze this function over here. So we have found the two functions to squeeze this function in between. Okay. Now what happened over here is the limit as x approaching to 0. This function above and this function below both have this limit to be 0. Now because the function above and below both approaching to 0 as x approaching to 0, so this function being squeezed by them will have the same limit here, which is equal to 0 by the squeeze thing. Okay. Now there's a hint for homework. We're trying to prove this limit equal to 0. Now you take a look here. This cosine of this 20 pi x, whenever you see sine and cosine, think about it as bounded above by 1, bounded below by -1, and then you will multiply x to the 4 power on each side of this double inequality. So this function over here is bounded above by x to the 4, bounded below by -x to the 4. And then you can go ahead and prove it. Okay. Okay, it's going to be very similar to the proof we have done over here. Okay. All right. So this is the end of section 2.3, and that's the end of our lesson today.